Okay, this is an early morning video. Let's hope this sounds okay. What we're talking about today is atomic structure. And you have some introduction into the structure of the atom. Our first model of the atom came from John Dalton. Dalton saw the atom as a solid structure. He did not know anything about the subatomic particles, but he did give us the law of conservation of matter. After Dalton came J.J. Thomson, whose plum pudding model discovered the electron. That was our first subatomic particle to be discovered. So we knew there were negative charges, just weren't sure about the location, the nature of the positive charge. It was Ernest Rutherford, with his gold foil experiment, that determined that the nucleus was actually a very dense and small positive component in the center of the atom structure. His problem was the electrons. The electrons, being negatively charged, should be spiraling around the nucleus, and the nucleus should be pulling those electrons in until the electrons and the nucleus would collide. The atom would implode. He didn't know how to explain why that wasn't happening. It was Niels Bohr who gave us the fourth model of atomic structure. And so in order to investigate Bohr's model, there's a number of things we have to do. We have to look at things like frequencies and wavelengths of light and understand the dual nature of light. To get into all of this, we need a lot of terminology. So we're going to go through this terminology very quickly so that we can discuss it and come to use it and understand it in class. We're going to be talking about quantum numbers. Quantum numbers is a set of 4 numbers used to describe the energy and the position of the electrons in the atom structure. If you look at the first of the quantum numbers, the first quantum number is called the principal quantum number, and it's given by the symbol a little n. The principal quantum number describes the energy level. This is going to show us the distance of that electron from the nucleus, and it's also going to tell us something about the energy of that electron. Let's take a look. What I have here is going to be a model of the atom, and in the center of the atom we're going to have a very small positive nucleus. Now, as we move out, we're going to encounter the energy levels. The first energy level might be here. Now it's going to go all the way around the nucleus. And remember, I'm drawing on a flat blackboard, so I'm drawing circles where what you should be envisioning is spheres, those energy levels moving all around this central nucleus. Most of what you see between the nucleus and the first energy level is just empty space. Rutherford realized that the main part of the atom is empty space. And so here's our first energy level that is closest to the nucleus. Now, as you go further out and encounter other energy levels, something happens. I'm trying to draw these in perspective because here is Bohr's first energy level. Then farther out you'll see his second energy level, and then the third. Notice that the space between the energy levels decreases as you move farther away from the nucleus. So, when we're talking about the principal quantum number, n can be 1, 2, or 3, and so on, designating the energy levels. The first energy level is going to be closest to the nucleus, the third energy level farther away. Now, not only does the principal quantum number tell us something about distance from the nucleus, it tells us something about energy. If you were looking at this diagram, what happens when you have a positive nucleus and a negative electron? Bohr says that those electrons have to exist on an energy level, that the electrons cannot exist here, or here, or here. They cannot exist in space, but they have to exist at certain locations. That's where you would most likely find those electrons. All right? So, if we have an electron in the first energy level, this is closest to the nucleus. We know that opposite charges, the negative electron and the positive nucleus, are going to attract one another. But Bohr says that as long as those electrons reside on an energy level, that they do not have to be pulled into the nucleus, that these electrons have energy associated with them. Not small, all electrons are small. An electron found in the first energy level does not have a lot of energy associated with it. Kind of think of it like a rocket ship. And if you have the positive nucleus, and then there's a little rocket ship with a small engine, it can only pull so far away from the attractive pull of the positive nucleus. So it's going to reside here. But if we had an electron with more energy, that electron could pull farther and farther away from the nucleus. It might even be possible, if an electron had enough energy associated with it, that it could leave the atom completely. So those electrons closest to the nucleus have the low amount of energy associated with them. And those electrons farther away from the nucleus will have a higher amount of energy associated with them. The principal quantum number tells us something about distance from the nucleus and the energy associated with that electron. Then, going back, the second quantum number is the orbital quantum number. Different textbooks use different names. I think your book calls it the angular momentum quantum number. When I was growing up and learning chemistry, it was called the azimuthal quantum number. But in all cases, it's been given the symbol a small l. This is going to tell us something about the sublevel and the shape of the orbitals, or where the electrons are residing. Here, we want to know that n equals L. So, if n is the first energy level, then there can only be one sublevel. N equals L. Let's look. On this diagram then, in the first energy level, there is only one sublevel. It's already drawn here. But in the second energy level, you would find two sublevels. We would have two different sublevels in the second energy level. And in the third energy level, three sublevels. And each of these sublevels are given a designation by a letter or a number. So if we're looking at this, the first sublevel is always going to be an S. There's a 1s. In the second energy level, the sublevel closest to the nucleus is the 2s. And in the third energy level, the sublevel closest to the nucleus is the 3s. Now in the second energy level, we have two sublevels. This would be an S and a P. Let's take a look then. Because if we're talking about our sublevels, the S's are the first sublevel closest to the nucleus in every energy level. S sublevels are described to be spherical. And I've drawn for you an example of what this would look like, where you have your nucleus in the center of the atom. And if we looked at our 1s sublevel, that 1s sublevel, here's my nucleus, that electron would be found at a certain distance away from the nucleus. And if we're looking at this in three-dimensional space, this would not be a circle, this would be a sphere where you would find that electron. If we were to move to the second energy level, however, that electron is going to be found in a sphere located farther away from the nucleus. And so this might represent our 2s on the board, where the 1s is a much shorter distance than the 2s is from the nucleus. All s's are spherical. Then if we go to the p's, if we wanted to describe the p's would be either dumbbell or figure 8 shaped. If you're looking at a set of axes, we talk about our x, y, and z axis. Now, when we're looking at the p's would be found then either along the x, so this might represent an x orbital. You can see that this x orbital is going to be dumbbell shaped. Not a great drawing there, but you get the idea. And if we have p in the y would be found here. This could be our p in the y representation. And then p in the z would be similar, but located along the z-axis. Now, what does this do? It means that if you're looking in three-dimensional space, that here is your nucleus, your p in the x would be located here along the x-axis, p in the y would be here along the y-axis, and p in the z would be here. If you were to do this modeling with balloons, what you would find is that this total volume would be equally filled. It doesn't make sense that if you're moving two electrons into the same space, that since they're both negatively charged, that they would be found at the same location. The first electron might be in the x position. A second electron, like charges repelled, would then be found in the y position. We'll be looking at this more. So we have our p orbitals. Notice that there would be only one s orbital, one sphere located at a certain radius from the nucleus, but there would be 3 p orbitals. We would follow this up with 2 more sublevels, the d and the f. D shapes are very complex, and F sublevels are even more complex. We'll look at pictures in our textbook. That's about it. Look at the pattern, however. If we look at this pattern, we're going to have 5 d sublevels, d orbitals, and we're going to have 7 f orbitals in the atom structure. 1, 3, 5, and 7. This can be shown looking at the magnetic quantum number. The magnetic quantum number is going to tell us about the orbitals. And to finish this video, I'm simply going to show you a pattern that we'll soon make sense of in class. When we're talking about the orbitals, here is our 1, representing the s's, our 3, representing the p's, our 5, representing the d orbitals, and then our 7 f orbitals. You might think about your p's as p in the x, p in the y, p in the z. Well, this will get us ready to do some work in class together and have some great discussions as we explore this further. This is just a good introduction that you should have in your notes.